So today I'm going to talk about tailings dam rehabilitation. I'm going to revisit that topic. And we're at the moment working, so I'm working with Mike Cole, which some people might know. We used to be at the University of Newcastle, but we're now in a private research company which researches restoration and rehabilitation of mine sites and the petroleum offsets. And we also work closely associated with Future Harvest, which is a vegetation services company. So, I'm doing this wrong. No, wrong button. Okay. Yes. So, tailings dams. So, I'm going to be talking about coal tailings dams, not metalliferous tailings dams. So, in the past, well, tailings dams are basically constructed areas where washery reject from washing coal, in this case, gets deposited and stored long-term for eventual disposal. So these tailings dams can be quite dangerous places. They're very swampy, they're like quicksand, and they have a series of characteristics which are quite difficult. They're usually left to dry and then capped with either spoil or soil to provide a stable surface, and then they either remain like that or something else might happen to them in the future. So the big issue with capping tailings dams is that, is that the weight of the material deposited in the dam forms a consolidation zone, so the weight of all the material deposits, and like, you know, when you do a sedimentation column and you get material deposit at the bottom, but you also get the formation of a crust, which then impedes the evaporation of water, which becomes trapped in between and forms a fluid zone. So this is really very dangerous because when you're either trafficking on this crust or when you're doing an activity like capping with machinery, for example, the vibration of this machinery causes the fluid zone to migrate to the surface and can cause substantial equipment or personal harm. So, and of course the other problem that can happen is that if this doesn't happen, the actual weight of the capping can express water and water will well up and you virtually have a swamp again. This obviously has really severe consequences in some cases. This is an example of a disaster in Brazil in 2015, where you see the before and after pictures of the rupture of one of these tailings dams, and you can see here where it's gone all the way downstream. People were killed, and it's a big issue. So making tailings dams safe, well, there's several approaches. You can just let it go to natural succession. That's not very safe. You can cap, like I've said before, but there are also sometimes issues with this. So we're proposing a kind of a mix of these two approaches, which involve developing a plant water pump, which hopefully will allow a more quick evacuation of the water. So how would this work? We're hoping that when we plant certain species of plants into the tailings dam, that these roots will be able to access the water table, access the water trapped underneath the crust, and that through transpiration of the plant, we'll be able to pump the water out from underneath these crusts. So what are these coal reject or coal washing tailings like? In the Hunter Valley, we're very lucky because the salinity is not very high in general. Most of them are low salinity, so they're pretty appropriate for plant growth. We don't have a lot of pyrites, so we don't have a lot of acidity issues. There's virtually no high quantities of heavy metals. It is, though, low in nitrogen and phosphorus, which can, of course, then lead to non-growth of plants. Other characteristics are the surface crust can be very hard, which can be like concrete and could potentially impede the growth of roots. It's often very dark in colour, causing high surface temperatures. And of course, these tailings dams, they're open, exposed, and very windy. And I have there a picture. You can see these plates and cracks of where the crust has dried, just like a mud pad. And you can see this plant here, you can see the wind damage that it's suffered. So can we actually grow plants in tailings is one question we asked ourselves already a few years back. In those days we were trialling native plants just to see if we could use tailings as a substrate to mix with other things to get plants to grow. And we trialled an OGM, which is a municipal waste product, and we trialled compost, which is a green waste product. And of course there's a tailings control there and a sand control. And you can see that average plant number. Plants can germinate in these materials. The higher municipal waste products were usually not very good because they're too high in nitrogen and phosphorus for working with native plants, and they were also prone to waterlogging. But the other treatments did relatively well until, of course, a bit further down, around about 5 months, where we started getting problems of competition in these pots. But we got some good results from that. We had a look at what the biomass was. So one of the things we calculated was, or we measured, was plant average shoot dry weight. And you can see here that the compost treatments and even the OGM treatments had quite high biomass. So we know that we can mix tailings now with compost and they will grow. But of course this is a pot scenario, showed us. So our next stage, of course, move these things into the field. So this is one of the dams we're working at. It's called Mangula. And we have at the moment set up 3 experiments. We're calling them the optimization experiment, the crack versus plate, and the species selection experiment. And these experiments have been funded by an ACARP grant, which will run for 3 years. We're half a year into the project. One of the first things we looked at was the safety of the personnel working on a dam, because, as I said before, these sites are very, very dangerous. If you do get liquefaction of the crust layer, you can certainly equipment can sink very quickly. Whether humans will sink, well, we'd rather not find out. So one of the approaches we've taken is to look at cone pressure resistance to try and establish some easily measured parameters which we can then use to designate areas where we can and can't walk to do our planting activities. So this graph basically shows depth and kilopascals, so pressure resistance along the top. And you can see here that the first 5 centimetres down to about 10 centimetres is where the crust is really hardest, and then very rapidly you get a loss of resistance and you get quite soft materials underneath. Oops, that's moved up slightly. So because we wanted to incorporate composts or some organic matter, we did, and we know that the crusts are very hard and not very suitable for root penetration. We did early on in this process look at using very small scale machinery to roughen up the surface a little bit to aid in the incorporation of organic materials. But we discovered very quickly that even only on such a very small scale, we had a loss of resistance. So this graph here shows depth again and loss of resistance on the top. So this was calculated using a baseline measure of cone pressure and then subtracting the loss of pressure after tilling. So we tried 2 different methods of tilling, and one of them wasn't too bad, but that was only a little bit like that. And then when we try to till a little bit deeper, we just get a massive loss to resistance. So we know now we cannot use any type of machinery on the rehabilitation, on the tailings dams. So one of the first things we looked, because we can't do this, was to have a look at using these cracks that form, because in the cracks we usually have much less resistance and the root penetration would be much easier than if we have the plants on the crack itself. On the plate itself. I don't have my words mixed up. So we did this small quick trial where we planted into the plate and into the crack. The plants were fertilised, and we were using Eucalyptus camaldumensis, which is the red river gum. It has properties which should allow it to survive in these kinds of environments because it tolerates flooding. It has large growth, which would allow it to be used as a pump species, and it also is tolerant to certain levels of salinity, although we don't have a huge amount of that here. We've run this experiment for 3 months, and there's really no significant differences yet because we planted just before winter, so we had high rates of survival. They haven't grown yet, but they are starting to shoot. There's no difference between the two treatments, whether they're planted in the crack or the plate. So apparently, at least over the winter months, there was no difference in these two. So we can plant in either of those two scenarios, we think. Because we want to use an organic material over the top of the tailings to alleviate surface temperature and also to encourage the accumulation of humidity at the soil surface. We set up this quick experiment which looks at 3 levels of fertilizer and 3 levels of mulch. But I don't have any results to present on that because we planted it quite late in the season and the plants have just not done anything over winter. So the next stage is looking at species selection for selecting species with high transpiration rates so that we can de-water these dams. So we've made a preliminary list of native species and species that are relevant to the area, with maybe the exception of Melaleuca quinquemonia, which is more coastal. And we've selected them based on parameters like waterlogging tolerance, salt level tolerance, and whether we could find information on transpiration rates. So this is just being planted in the field now. There's species that have been blocked out nicely, and then two densities will be trialled, and they will all get an application of fertilizer and mulch. So the idea with this then is once the plants are established and growing nicely, we will start to develop species models for transpiration rates, and we'll be using primarily a portable photosynthesis system to measure the transpiration rates under different conditions like light levels, relative humidity, and a series of other parameters. We're also hoping, with the information we gather, we'll be working at another dam also. We'll be hoping to model the different responses in the different types of dams. So the potential project outcomes. We're hoping, of course, to create safer tailings dams. We hope to have improved water management, speedier drying of these dams, and safer capping conditions. But we would also like to look at future land use or alternative land use options, which would include growing soil, for example, which could be used as on rehabilitation sites when there is a lack of natural soil. Growing communities of plants, which could also be transferred onto rehabilitation sites. Growing forestry trees, for example, could also be used. And of course, additionally to that, we hope to increase the overall knowledge of Australian native plant species, looking at physiological and health profiles and physiological tolerance levels. And I'd like to acknowledge our funding source, which is the Australian Coal Association Research Program, and the ACART Monitoring Committee, Rainwater Mine, and West Wallsend Mine, which is the other mine for which I haven't shown any data. Thank you very much.
Thank you very much, Carmen. It's 3:15, so
Lovely.
we will move on. So second up is a speak from Huang.
Thanks very much. It's great to be here today, and I planned to be here for 3 days but only made today, but I've been overwhelmed but also inspired by what I've heard. I'll be coming at this matter of ecological restoration from a different angle from most of the talks I've heard about today, or a different end. And this more sits at the policy or legislation end and establishing guidance rather than the practical hands-on side of things, which I've heard more about today, which has been quite wonderful. I work for an ecological consultancy that mainly deals with impact and offset assessments for a whole range of proponents across the country, together with a whole range of other studies that we undertake. But one of the areas that we work in quite a lot now is offsetting and the theory behind using mine rehabilitation as an offset. And there's a lot of work to be done in this area. However, we've been successful in securing an ACARP funded grant, the same as Carmen just referred to, or a different grant but the same body, to undertake an investigation into this. So we all know that mining often has unavoidable impacts on biodiversity. There is usually some small degree of scope to avoid impacts, but a resource is located where a resource is, and it's more about the infrastructure and overburden and placement areas that do have some room to move on mining projects, often, but not always. But usually, more often than not, there is an impact on biodiversity. Biodiversity offsets are normally required under the legislation that we operate under in most jurisdictions across Australia. And these are typically land-based, or they have been up until now at least. And there is, of course, who would have thought, a decreasing availability of land-based offsets, and obviously that's going to become more challenging in the future. And there's always a degree of controversy and disagreement about how land should be used in different locations. There is obviously has been a growing requirement over the years by regulators for mine rehabilitation to move on from simply setting up safe and stable landforms to having vegetation that is long-lasting, it will be permanent, it will be able to, I guess, as a type of vegetation that might be on a site, change and continue to provide stability and safety, but also biodiversity outcomes. That thinking obviously has come through over the last couple of decades. And through the overlap of these things, there's, in my view and that of many, an opportunity to maximise biodiversity outcomes through impact avoidance and minimisation on mines, of course, but also through rehabilitation and offsetting, and that's the area that I'm working in at the moment. So, central question, I guess, is whether or not ecological mine rehabilitation, I'm just using that very generic term at the moment, whether that can meet offset requirements. Offsetting itself, using mine rehabilitation, is permitted through legislation and policy in Queensland, Western Australia and New South Wales, and maybe in some other jurisdictions that I'm not as familiar with, such as the Northern Territory and South Australia, I'm not sure. At the Commonwealth level under the EPBC Act, these are being assessed on a case-by-case basis. Their environmental offsets policy neither permits nor disallows mine rehabilitation to be used as an offset. There's substantial older coal mine rehab that exists around the country, predominantly in New South Wales, Queensland and Victoria. And very little, if any, of this has been established with the rigorous requirements around establishing recognisable plant communities and ones which have an expectation or an anticipation that they will be self-sustaining plant communities, self-sustaining recognisable plant communities in the long term. In a range of jurisdictions in the country, including New South Wales, where my primary focus is, there are now metric-based approaches used to calculate impacts and offsets for biodiversity, such as the BAM, Biodiversity Assessment Method, which is about a year old in New South Wales. Obviously, ecological improvement and its success or otherwise in offsets and in rehab needs to be measured and reported on, evaluated and reported on. Government and community are requiring a high level of certainty around these things than they have in the past, and there's more scrutiny and there's increasing transparency. And mining proponents, of course, they're there to do their job of mining, extracting material and what have you, but they're becoming increasingly savvy around the legislation and offsetting, and they obviously want to maximise their return but limit risk, but also one of the risks to their operation is their, I guess, their license, their social licence to operate, and that includes biodiversity matters and how they're performing. So just very briefly, in terms of the two jurisdictions that my study is mainly operating in, and that's New South Wales and Commonwealth, I'll come back to that in a moment. In New South Wales, offsets are required, biodiversity offsets, required to secure and establish or enable the recovery of known plant community types, or PCTs, that are listed under a state classification system, and or threatened ecological communities that are listed by the New South Wales Scientific Committee. And each of those has a suite of descriptors that indicate what is a PCT or a TEC, a threatened ecological community. In New South Wales, offsetting effectively deals with all biodiversity that's impacted. I know that's a generalisation, but all of the things that are measured, by and large, apart from a few things that escape underneath the threshold, have to be offset. Whereas at the Commonwealth level and a range of other jurisdictions, it's only threatened entities that require offsetting. So in New South Wales, is a much broader grab in terms of what is required to be offset. And also in New South Wales, there are now 4 options around offsetting. One of those is establishing land-based offsets using the credit system that I spoke about. But you can also pay into a fund administered by a government semi-authority, which then has to go and obtain the land itself under strict requirements. So the mining proponent can just pay into that fund and walk away, effectively. It's expected there'll be a premium for that, but it's not known at the moment because the market is very young. One of the options a third option is ecological mine rehabilitation for mining projects. At the Commonwealth level, what are known as matters of national environmental significance, or MNES, are the things that require offsetting, not all of the biodiversity, and they're typically threatened species, threatened ecological communities and migratory species. And as I stated before, offsets at the Commonwealth level are largely land-based at this stage, although there is a review of the EPBC Act to commence next year. So the study that we've embarked on, and we're about a third of the way into it, and we will hopefully be reporting our outcomes around this time next year, with any luck at a suitable conference or otherwise. We're attempting to investigate ecological mine rehabilitation success in the broad sense. The study has eventuated because of several years of investigation by some of our partners in this study. That's the New South Wales Minerals Council, which is the umbrella body for mining in New South Wales, Glencore, one of the largest coal mine operators, and my firm, into the suitability of ecological mine rehab in the Hunter Valley. And that's in relation to some state and Commonwealth requirements around those vegetation types and threatened ecological communities, and whether or not mine rehab might be one avenue, one of a number to meet offsetting requirements. It's also been influenced by certain recent coal mine project approvals, or those subject to approval at the moment, where the Commonwealth has expressed an interest in allowing a certain level of ecological mine rehab to be established as an offset for the project. We sought funding and we were successful under the Australian Coal Research Limited funding avenue. And we have in-kind support from some of the large mining companies, Glencore and Yancoal in particular, and the Minerals Council, but also Peabody and Idemitsu. And they collectively run a large number of mines in New South Wales and Queensland, coal mines in New South Wales and Queensland in particular. The aim of our study is to provide guidance to industry on the rehabilitation of coal mine sites around establishing, and these are our most important words in the whole thing, recognisable and self-sustaining vegetation types. And they need to include threatened ecological communities. There's a difference between the two. We're focusing on open cut coal mine sites, particularly in the Hunter Valley in New South Wales, but also in terms of our data collection more broadly in New South Wales and in Queensland. We want to the best extent that we can, we want to ensure that our findings have a more relevant at the national level as well for coal mining, open cut coal mining. And we're looking into temperate woodlands in particular, and especially EPBC listed threatened communities. In terms of our objectives, we're seeking to determine if rehabilitation can establish, recognising and self-sustaining vegetation types and TECs, and as a side issue, can it establish suitable habitat for threatened fauna? And that will be a specific subset of threatened fauna listed under the Biodiversity Conservation Act in New South Wales, and most likely woodland birds, given the time and funds that we've got. We will most likely need to focus on more detectable species. We're seeking to develop some, if not all of these, or aspects of each of these, performance and completion objectives and criteria, and the SMART monitoring guidance around rehabilitating native veg types and TECs. And we're just at the phase where we're determining which of those we can focus on, which we might cooperate with some other organisations as well who are investigating this area. The outcomes, of course, must be practical and cost effective in relation to their implementation for the mining companies. So we need to work within the legislative framework because the coal mines are seeking approvals under those legislative frameworks. We're hoping that the project, when it results, will help to incentivise quality ecological rehabilitated coal mine sites so that mines will have better guidance on how to establish these communities, or certainly the parameters that are required to establish them and report against their success or otherwise. And that through this and allowing or encouraging offsetting, there will be a greater re-establishment of plant community types and TECs in mining districts and create large interconnected areas of habitat rather than just simply pasture. Our study area is really these mines that I'm putting up here. So in this image, I'm not quite sure which the pointer is, but down at the bottom right, you might just see there Newcastle, Sydney is south of there. Most of those mines are in the Hunter Valley or west of there. We'll be focusing primarily on Mangoola mine, which is where Carmen spoke about previously. We'll have a particular focus on the central Hunter Valley eucalypt forest and woodland, and the white box, yellow box, black list, red gum woodland and dried native grasslands, both listed as critically endangered under the EPBC Act. We'll also be collecting data, existing data from Boggabri coal mine, which is in the Gunnedah mining district. Both of these mining districts have a substantial number of mines and mining impacts. So we're currently sitting between stage 1 and 2 at the moment. We've undertaken a review of literature, legislation, policy and guidelines, etc., although there's still more coming in that we weren't aware of. We're about to embark on an analysis of the data that we have obtained, and we are, I guess, preparing now in consultation with others the precise aspects of the project that we think we can invest in over the next 9 months. And then either late this year, a bit drought affected, or in autumn next year if it's better, but you know, who can tell, we'll be undertaking our own targeted site surveys at between 2 and 4 mines in the Hunter Valley to collect data in accordance with the New South Wales BAM methodology and the other data that we think are necessary to inform our work. So finally, I've already mentioned some of this, but we are currently working on, under a framework that's operating in New South Wales where ecological rehabilitation objectives are being established by the government at the moment. We expect them to be published in the next 2 months, and subject to that we can tweak precisely what we're working on under those objectives in relation to completion criteria, monitoring guidance, and also establishing guidance on setting up a reference site framework in the Hunter Valley to compare ecological mine rehab against. So hopefully in 12 months' time we'll have our outcomes, and like I said, I'll be able to report on them. But my details will be available on the conference website, I imagine, and I'd certainly welcome any feedback that anyone has from the range of experience and disciplines that you operate in. Thank you very much.
Thank you, sir. Yes, and so we'll move on to our third presenter, who is Hamid Amir from New Caledonia. I think he's going to give us a 30-year plot in under 15 minutes. Thanks.
So my talk is about a project called Le Concept, which is financially supported by CNR Technical et son environnement in New Caledonia. And I will treat the synthesis part of 30 years of ecological restoration of mining-degraded areas in New Caledonia with production of success indicator. It was produced by two research teams and two private companies listed here. Oh, sorry. New Caledonia is a small country, but there is now here 3 nickel factories, which increase a lot mine surfaces and degradations of the valuable ethnographic ecosystems. The ecological restoration of these areas is very difficult because of the extreme conditions of soil and water availability. And after having tested other approaches like pine plantations and use of gregarious species like, Acacia, spirorbis, and Acacia, the rehabilitation in ecological restoration perspective began in the 90s with lots of experimentations and practical vegetation programs. We have here an example. So we can, the results were very scattered, and there was no synthesis done and no clear information about the evolution of these vegetated areas. Reconsent project aimed at the statement of highly diverse situations of vegetated areas. Here we have some examples. Vegetation on banks of waste rock piles. Here, vegetation on flat area on saprolite. Vegetation on topsoil with plantations, and hydroseeding with the topsoil. The questions addressed here are what techniques and practices were successful, and what indicators could we use for the evaluation of restoration success. For doing this, we listed 381 revegetation sites with, after obtaining a few characteristics of the sites, and then we pre-selected 63 sites using these criteria, and then we visit these sites to have more information, and finally selected 35 sites using more criteria to keep all the diversity of the situations, substrates and techniques. For example, we chose sites vegetated at different years and different numbers of plant species used, and reuse or lot of topsoil, and variations in amendments, presence or lot of nitrogen-fixing plants, etc. Here we have the different, the 35 sites all around the mainland of New Caledonia. The project created the permanent database, which was incremented progressively. Here we have 2 screens of this database. The project is an integrated approach with the contribution of a statistician to analyze correctly all the results. And we also produced a field study form to quantify and qualify the current states of the sites for all the parameters that can determine the restoration success. The field study form takes into account 3 types of parameters: system productivity with different parameters, system dynamic over time with other parameters, and integrated complexity, interaction complexity. The first page of this form is for general information and the characteristics of the parcels and the substrates. The second page concerns the substrates and the erosion and the ecosystem surrounding the vegetation site. The third page corresponds to the characteristics of the vegetation with different characteristics, and this done with 5 quadrants for each site. And the final page corresponds to surface covered by the vegetation and health status of the vegetation. The synthesis part of this project is global mathematical approach to detect the parameters which contribute to the success of the restoration. We studied 25 variables measured for the 35 sites. Actually, the 35 sites correspond to 67 different modalities or treatments, which are listed here. We performed factorial analysis of mixed data, taking into account qualitative and quantitative variables, and then we performed essays to appreciate the contributions of the different variables. As there is a huge heterogeneity of the site characteristics, we needed to classify the different sites with the clustering approach. So we obtained 3 clusters, one in black here, in red, and in green. This is a projection in the 2 axes of these 3 clusters. Each of these clusters have different, was determined by different variables, which are listed here. Some of them, some sites are with a high rainfall, others with low rainfall. Some are with flat areas, others with banks, some with windy places, and others with less windy, etc. Now searching for synthetic indicators of ecological restoration success, we performed PCA for each cluster, and we can see here that all of the ecological and biological variables are oriented towards the axis 1, the direction, the positive direction of axis 1, so that the projection, the orthogonal projection of all these parameters and their addition could be a good evaluation of the productivity, diversity, and dynamic of the system, so they could represent an ecological restoration synthetic indicator of success. So we applied this model to the three clusters. Here we have the cluster 1, which was divided in three subclusters. The subclusters are clearly distinguishable with a significant difference between them, and the green one has a better success for restoration. Here we have the ranking of all the modalities of this cluster, and this is an example of good restoration corresponding to this point. So we have done this for the three clusters. Here the cluster 2, also with a ranking of all the modalities, as we have seen for the cluster 1. Naturally, we wanted to know if the mathematical model corresponds to what we can see in the field. And here we have three sites with clearly different grades in our model, and you can see that this bad grade corresponds to nearly desertic zone. This good grade corresponds to a dense and diverse system, and this is an intermediate. The ecological restoration of indicator of success was computerized and will be accessible in the web for companies and communities, and they have just to fill the field form and to fill this table here, and they give them a success indicator, a grade with the point in the map. Main conclusions: the global approach of the Reconcile project enable us to develop a multi-factor success indicator. We found that about 20% of the vegetated sites tested were in a good evolution toward complex ecosystem, but they will reach after probably 15 to 30 years. Other 30% will evolve more slowly, but will probably reach the target after several decades. The other vegetated areas will probably need new operations to reach the target. Finally, we found that sites which had low grades were generally characterized by the failure to take into account important practices. For example, there were no topsoil or no organic amendments added, and not enough seed germination. And my colleague Bruno will now develop this part. Thank you very much.
So we're going to go back to New Caledonia with my good friend Bruno, who's going to continue the 30-year journey for us. Thank you, Bruno.
So, good afternoon to you all. I'm Bruno Fogliani, as I said Peter. I'm Deputy Director and Researcher at the New Caledonian Agronomic Institute. And the work I will present to you today focuses on comparative analysis and recommendation outcoming from a study of 30 years of ecological restoration of mining-degraded areas in New Caledonia. So my colleague Hamid Amir already present you some elements of this project, but for those who were not here, just a few reminders. As you all know, New Caledonia is situated not so far from Australia. You can come and visit us. It's only 2 hours and a half from Brisbane. New Caledonia is considered as a biodiversity hotspot, and present a high endemicity rate with various vegetation for a so small island. Several reasons explain this fact, including climate, isolation, and soils. The ultramafic soils, in particular, which are represented here, are poor in nutrients and rich in heavy metals, and they occupied about 30% of the main island. And that has led to a speciation. As you can see, 66% of the flora grow on this kind of soils, with an endemicity of about 80%. And about 1,100 species are obligates from this soil. Unfortunately, like everywhere, there are several threats, including nickel mining activities that led to degradation. Regarding mining activities, it is evaluated that 20,000 hectares have already been degraded by mine, and that 100 are destroyed each year. So during the last decades, many revegetation projects on ultramafic areas degraded by nickel open cast mining operation were done. So it is necessary to realize a practical synthesis review to determine both the state of now in this domain and to determine the most effective techniques and also to guide future researchers. So it was the aim of this project. So I will not develop the methods as my colleague already done, but just remind that it has consisted in evaluating 35 restoration operations, reflecting the maximum diversity of field conditions and techniques used to establish recommendations. These 35 operations represent at least 67 operating procedures, and several parameters were recorded. For that, random plots, as you can see here, with variable size depending on the surface of the restored area and also on the used method. Here you have two methods, the plantation and hydroseeding. These plots have been placed on different studied zones, and several variables were measured to evaluate the ecosystem productivity and dynamic. Here you have some examples of variable, and in fact it was based on the 34 variables that were calculated or directly obtained from field measurement, and from this variable stochastic algorithm permitted to select 12 variables which have the most significantly effect to compare the different used treatments. And the result analysis was performed with hierarchical classification applied on ordination. So to illustrate it, I will present you in detail the result for the topsoil effect case, and then more synthetically for other case studies. So first, for the topsoil, the objective was to evaluate if its use has a positive effect on restoration. For that, 4 different zones with different operating procedures were used. You can see their location here on the map. And here you have a detailed table of their year of achievement, altitude, slope, substrate, etc., including the number of species that were used, planted here because it's a plantation. The analysis results of the field survey show the 12 most significant variables here for this case that influence the restoration success, response, and their representation by projection. Finally, the projection of the different studied plots clearly indicated the effect of the topsoil, as the blue cluster biological variables that represent zones without topsoil have values lower than those of the orange cluster that represent zones with the topsoil. A more detailed analysis permitted to highlight that whatever the considered variable, the modalities with topsoil has always higher value, here represented in red each time. In particular, higher density of individuals belonging to the following list of plant family there, that I will not develop too long. They also present a greater diversity of species that appear on the zones. These species can either come from the topsoil seed bank and also from seeds of individuals from the surrounding environment. Also, there is a most important survival of planted individuals on modalities with topsoil, and their size are always higher, here represented in blue, for several species. So it's particularly due to the physicochemical and microbiological composition of the topsoils. The topsoil also promotes the reproduction of plants and strongly increased the diversification of plant species. So it appears necessary and essential to use the topsoil to ensure the success of ecological restoration, and it has to be systematically used when it is available. It must be used continuously, means spread out directly after its collection with the shorter storage period. A guide for its use was established for practitioners. We also studied the effect of substrate in absence of topsoil on two zones presenting several operating procedures, mean different substrates like saprolite or laterite, yellow or red, or for those of you which are not familiar with the ultramafic soils, here you can see the weathering profiles of the ultramafic soils with first on the topsoil, and then the red laterite, the yellow laterite, the saprolite, and finally the mother rocks. So the analysis showed that laterite, in particular the red one, is the most favorable, with a higher survival and growth of the planted species and a higher plant recruitment. It also appears significant effect of the amount of stone in the substrate. And finally, a species affinity was found and permitted to establish for the first time a list that will need to be completed, affinity to the soil. After that, regarding for the effect of fertilizer and amendments on plantation, 3 zones presenting several operating procedures mean different inputs of organic matter or chemical fertilizer were used. And the results confirm here, because in some zones you have topsoil, they confirm that the use of topsoil is full of benefits, both on survival and growth, and it's better with the addition of inputs. Otherwise, laterite is still a solution added with inputs. It also appears that organic matters give better results and has to be encouraged, but with clearly established rules. For example, sludge needs to be used in the planting hole instead of being sprayed to avoid the appearance of exotic species. We also evaluated the wind exposure effect using 2 zones, exposed or not to the dominant wind coming from southeast, on which there was a use or not of vegetal windbreak. It showed that exposed zones are less favorable and present a less diversity, essentially composed of herbaceous plants. So plantations have to be realized preferentially in zones sheltered from the wind, and for the exposed zones, the use of windbreak is necessary and need to be planted previously or made of large individuals. We also compare 2 methods, the hydroseeding and the manual seeding, with topsoil, with or without a scratching of the soil before the topsoil spreading. So it showed that there was no significant difference between the two methods. However, scratching appears to be of interest to enhance the restoration success with more ligneous species diversity, both with cyperacid. Whatever the used method, it appears that results still low in success and can be certainly enhanced if a regulated seed sector is implemented. Finally, the last important analysis concerned the case of Acacia spirorbis, a species that was and still largely used in revegetation program in New Caledonia, but appears to be gregarious. So we studied 9 zones with different densities of planted acacia on different substrates with other native species between 2 and 38 species. Just to indicate that the exact density of acacia used in plantation was rarely available. We evaluated in the field. We evaluated it in the field using living plants. So results show that zones with highest density in acacia are more widely characterized by high productivity of the ecosystem values, defined by the better index of plant cover and a better growth of the woody species, but it includes the acacia itself, which represent at least between 40 to 90% of the ligneous plants. On the other hand, the dynamics of the ecosystem is less favorable. Finally, the presence of topsoil promotes the establishment of native species under the cover of acacia, but the evolution of the system seems to be blocked. So Acacia spirorbis in high-density plantation has to be avoided for ecological restoration, as the system led to a monospecific trend. In contrast, the zones with medium to low density of acacia have a lower but sufficient productivity of the ecosystem and present a better dynamic both for the total number of individuals, total number of recruitment, and a high species diversity. It plays a role of facilitating plants and it enriches the soils in organic matter, especially nitrogen. It remains to check if the acacia won't block the system and if it will need to be cut in the long term if it not dies. Also, use of other facilitating species within the leguminous family has to be considered, and positive impact of gymnostoma species from the Casuarinaceae family has to be studied. So to conclude, this project has permitted to establish a technical guide for ecological restoration on ultramafic environment in New Caledonia, permitted also to establish an indicator of the ecological restoration success, and at the same time, the developed database will permit to collect all precise information of future restoration projects and their survey, and will certainly be used in several years to optimize more and more the ecological restoration. And finally, the gap highlighted permitted to consider a new research project, and the next step for us is to adapt the SERA standard to New Caledonia. But as a first step, I just be informed that the SER standard has been translated in French and are accessible on the SER website. So thank you for your attention.